Imagine a world with no blue oceans, no green forests, only a blinding white sphere drifting through the cold silence of space. This was not a distant alien world. It was Earth. The Great White Silence. Imagine a world stripped of its familiar blue and green, reduced to a silent monochromatic desert of ice. Around 700 million years ago, during the Cryogenian Period, our planet underwent a transformation so absolute that it challenged the very boundaries of what a living world could be. To an observer looking down from space, Earth would not have appeared as the vibrant, swirling blue marble we know today. Instead, it would have resembled a blinding, featureless sphere of white, glinting coldly in the faint light of a young sun that was still 10 to 15% dimmer than it is now. This was the era of Snowball Earth, a time when glaciers did not merely crown the poles, but marched relentlessly across the continents, plunged into the oceans, and eventually seized the equator itself. For decades, the scientific community struggled to accept that such a state was even physically possible. The idea that a planet covered in oceans could freeze entirely and then somehow wake up from its icy slumber seemed to violate the basic laws of planetary stability and climate feedback. It was assumed that once a planet froze to this extent, it would be locked in a permanent, irreversible death grip, reflecting so much sunlight that it could never warm up again. Yet, as geologists peered deeper into the ancient rock record, they began to uncover unmistakable global signatures of this ancient freeze. They found glacial tillites, scrambled mixtures of mud, sand, and boulders ground up by moving ice sandwiched directly between layers of tropical limestone. These bizarre rock formations, found in places as far-flung as Namibia, Australia, and the Canadian Arctic, offered a startling hint. The warmest, most tropical sanctuaries of our world were once buried under sheets of ice up to a kilometer thick. This was not a typical ice age, but a planetary crisis that endured for tens of millions of years, testing the absolute limits of life's resilience. The Runaway Engine. How does a warm, ocean-bearing planet slide into such an extreme state of deep freeze? The answer lies in a delicate balance of geology, chemistry, and sunlight balance that was radically disrupted during the late Proterozoic. The story begins with the slow, tectonic breakup of an ancient supercontinent called Rodinia. For hundreds of millions of years, Rodinia had sat as a massive landmass centered largely around the equator. As tectonic forces ripped this supercontinent apart, it created vast new coastlines and shallow seas. This newly exposed land was positioned in the wettest, warmest parts of the globe, where rainfall was high. This geographic arrangement triggered an unprecedented acceleration of a process known as silicate weathering. Rainwater, falling through the atmosphere, absorbed carbon dioxide to form a weak carbonic acid. When this rain fell upon the basaltic rocks of the breaking continent, it reacted chemically with the silicate minerals, breaking them down into calcium and bicarbonate ions. These ions were washed by rivers into the oceans, where they combined to form carbonate sediments that settled permanently onto the seafloor. In effect, the Earth's natural thermostat was turned down. By scrubbing vast quantities of carbon dioxide from the atmosphere, the weathering of Rodinia slowly starved the planet of its primary greenhouse gas. As the atmosphere thinned of its warming gases, temperatures plummeted. Glaciers began to grow at the poles and creep downward toward the mid-latitudes. This movement triggered a second, far more dangerous mechanism, the ice-albedo feedback loop. Ice is highly reflective. It bounces up to 90% of incoming sunlight back into space, whereas open water absorbs most of it. As the ice sheets expanded, they reflected more solar energy, cooling the planet further, which in turn allowed the ice to grow even faster. Once the glaciers crossed a critical threshold estimated to be around 30 degrees latitude, the feedback loop became unstoppable. The planet had entered a runaway state, freezing itself alive in a matter of thousands of years. The grip of the ice. With the runaway feedback complete, Earth entered a state of profound, eerie stagnation. This was the Sturtian glaciation, which began around 717 million years ago and lasted for an astonishing 57 million years, followed millions of years later by the shorter but equally intense Marinoan glaciation. During these intervals, the planet was locked in a cryogenic grip. Temperatures at the equator fell to match those of modern-day Antarctica, averaging -50 degrees Celsius. The hydrological cycle, the great engine of evaporation, cloud formation, and rain ground to a near total halt. Without open water to evaporate, the atmosphere became incredibly dry, and snowfall dwindled to a whisper, leaving vast wind-swept deserts of ice and bare rock. Underneath the thick ice sheets, the oceans became dark, silent abysses. Cut off from the atmosphere, the water could no longer exchange oxygen with the air. Over millions of years, the dissolved oxygen in the oceans was slowly consumed by the decay of organic matter, turning the deep seas completely anoxic. This lack of oxygen allowed dissolved iron, carried by submarine volcanic vents, to accumulate in massive quantities. When the oceans finally met oxygen again, this iron precipitated out, forming what geologists call banded iron formations, unique rock layers that had not been deposited on Earth for over 1 billion years, serving as a silent testament to a suffocated ocean. No sunlight touched the deep sea, and the physical world remained frozen in time. A silent monument to a climate system that had run off the rails. The Slushball Debate. As the evidence for this ancient freeze mounted, scientists found themselves divided over the true nature of the ice. How could life have survived if the entire planet was encased in a solid, unbroken shell of ice up to a kilometer thick? This question gave rise to the Slushball Earth versus hard Snowball Earth debate, a scientific controversy that continues to shape our understanding of the Cryogenian Period. Proponents of the hard snowball model argue that the climate physics are clear. Once the ice-albedo feedback takes over, the entire planet must freeze solid, including the equatorial oceans. In this scenario, the planet was a pristine white billiard ball, sealed completely from the atmosphere. However, paleontologists point out a major flaw in this model: the fossil record. They argue that photosynthetic organisms, such as green and red algae, survived this period without undergoing a mass extinction. Photosynthesis requires sunlight, which cannot penetrate ice sheets hundreds of meters thick. To reconcile this, the slushball model proposes that a narrow band of open water, or at least very thin, seasonal ice, persisted around the equator. This open water refuge would have allowed ocean currents to continue circulating, transferring heat and allowing sunlight to penetrate the water column. This debate highlights the challenges of reconstructing ancient climates. Scientists must balance the mathematical elegance of computer climate models with the messy, physical reality of fossils preserved in stone. Whether the Earth was a hard snowball or a slush ball, the reality remains that the planet was pushed to the absolute edge of habitability, forcing early life to adapt or perish. Life in the cracks. Before this global freeze, Earth's oceans were populated by simple multicellular algae, amoebas, and diverse lineages of single-celled bacteria and archaea. These organisms lacked the complex structures of plants or animals, yet they were the guardians of the planet's evolutionary future. When the ice closed in, it seemed that life's brief experiment on Earth might be snuffed out entirely. Without sunlight, photosynthesis, the foundational process of the biosphere, was nearly impossible across most of the globe. Yet, life did not perish. Instead, it retreated into ingenious, localized sanctuaries. One of the most critical refuges was found in cryoconite holes. These are small, dust-filled depressions that form on the surface of glaciers. Wind-blown dust, dark with minerals and organic matter, absorbs solar heat more readily than the surrounding white ice. As the dust warms, it melts a vertical pocket down into the glacier, creating a tiny, liquid water micro-oasis. Inside these isolated meltwater pools, communities of photosynthetic cyanobacteria and green algae survived, insulated from the extreme cold and nourished by the trapped minerals. These microscopic ecosystems would have been incredibly hardy, slowing their metabolic processes to survive the long, dark polar winters. Deep beneath the ice-choked oceans, another sanctuary existed: hydrothermal vents. Along the mid-ocean ridges, volcanic activity continued unabated, spewing superheated water rich in sulfur, iron, and methane into the dark depths. Here, far from the reach of sunlight, chemosynthetic bacteria thrived, converting toxic chemicals into organic energy. These volcanic oases supported complex microecosystems that were entirely independent of the frozen surface world, acting as evolutionary incubators. Additionally, tidal cracks and hot springs near volcanic islands provided transient zones where ice fractured, allowing fleeting glimpses of sunlight to reach shallow waters, keeping the spark of photosynthesis alive. It was a fragmented, threadbare existence, but it was enough to keep the flame of life burning. The Great Thaw. For tens of millions of years, the icy prison seemed permanent. The weathering of rocks had ceased because the continents were buried under glaciers, meaning there was no liquid rain to wash carbon dioxide out of the atmosphere. But deep beneath the ice sheets, the tectonic engine of the Earth was still churning. Volcanoes continued to erupt, venting massive quantities of carbon dioxide, water vapor, and sulfur dioxide into the atmosphere. In a normal world, this volcanic carbon dioxide would be scrubbed from the air by rain and rock weathering. But on a frozen Earth, this carbon sink was broken. The gas had nowhere to go. It began to accumulate in the atmosphere, molecule by molecule, century after century. For 50 million years, the atmospheric concentration of carbon dioxide climbed steadily, eventually reaching levels hundreds of times higher than those of today. The greenhouse effect of this massive carbon dioxide blanket began to trap heat with immense efficiency. Yet, because the ice reflected so much sunlight, the planet did not melt immediately. The atmosphere had to reach a tipping point, a state of extreme thermal tension, where the greenhouse effect finally overcame the reflective power of the ice. When the temperature finally rose enough to begin melting the equatorial ice, the process reversed with terrifying speed. As the ice retreated, dark water was exposed, absorbing more sunlight and accelerating the warming. The global freeze dissolved not in a gentle spring, but in a violent, chaotic super-greenhouse transition. Within a few thousand years, the frozen desert became a torrential, boiling world of storms. Acid rain, fueled by the massive buildup of atmospheric carbon dioxide, fell in torrents, chemically weathering the newly exposed rock. This process washed vast amounts of calcium and carbonate ions into the oceans, rapidly depositing thick, distinctive layers of limestone known as cap carbonates directly on top of the glacial tillites. These rock layers, which we can still touch today, stand as geological monuments to the most violent climate shift in Earth's history. The Cambrian Catalyst. The sudden melting of the global ice sheets unleashed an environmental revolution. The torrential rains of the post-glacial world washed vast quantities of weathered continental rock into the oceans. This runoff was rich in nutrients like phosphorus, calcium, and potassium elements that had been locked away or ground to dust by the grinding weight of glaciers for millions of years. This sudden influx of nutrients acted as a massive dose of fertilizer for the surviving marine life. Photosynthetic algae and cyanobacteria experienced an unprecedented boom, multiplying in the warm, nutrient-rich coastal waters. As these organisms flourished, they released staggering amounts of oxygen into the atmosphere and oceans. The long-starved deep seas were suddenly oxygenated, creating new ecological niches and fueling the metabolic demands of more complex. This dramatic transformation of the environment is directly linked to one of the most significant events in the history of life, the emergence of the Ediacaran biota and the subsequent Cambrian explosion. Out of the crucible of the frozen apocalypse, life emerged not weakened, but fundamentally reorganized. The intense evolutionary pressure of surviving in isolated, high-stress refuges, organisms had developed sophisticated cellular machinery to cope with extreme temperatures and fluctuating chemistry. With a sudden abundance of oxygen, animals could now synthesize collagen, a crucial structural protein that requires high levels of oxygen to produce. This allowed for the development of larger bodies. When the world warmed, these diverse, resilient lineages expanded into the newly opened oceans, giving rise to the first complex animals with eyes, limbs, and predators. The ice had not destroyed life. It had acted as a profound evolutionary filter, forcing life to adapt, cooperate, and ultimately diversify in ways that would shape the future of the planet forever. A fragile balance. The story of Snowball Earth is a profound reminder of the delicate feedbacks that govern our world. It demonstrates that the climate of a planet is not a static backdrop, but a dynamic, living system shaped by the interactions of geology, chemistry, and biology. The very existence of life on Earth today is a testament to the resilience of those microscopic organisms that clung to survival in the dark, frozen cracks of a hostile world. As we look out at the icy moons of our solar system, like Jupiter's Europa or Saturn's Enceladus, we see worlds that are locked in permanent, global ice sheets. The lessons of our own planet's deep past suggest that beneath those frozen crusts, life may well be holding on, huddled around hydrothermal vents or suspended in icy fractures, waiting for its own day. On Earth, the balance between fire and ice remains a delicate dance. Understanding how our planet froze and how it managed to wake up is crucial to understanding our own place in this precarious, beautiful cosmic oasis. The survival of our ancestors through the cold darkness of the Cryogenian tells us that life, once established, it adapts, it finds the cracks, and it waits for the light to return.